Hi, this is the fourth FRQ on the AP Physics C extra credit videos. So here the physics fact. The most important physics fact we need to know, Newton's second law, sum of forces, stuff that makes it go minus stuff that holds it back, equals mass times acceleration. And then we also need to have good lab knowledge and just really think this problem through. So the first question is to briefly identify each quantity to be measured, the symbol used to represent that quantity, and the equipment that would be used to measure the quantity. So think about how you're going to conduct the experiment, get an idea, and then think about the equipment you're going to need. So I wrote mine. I said mass. Oh, and keep in mind there are some stuff we must use, and then we'll also have equipment that's typically found in a high school lab. So I said we need the mass of M1. We're going to measure that with an electronic balance. Mass of M2, electronic balance, and mass of M, the additional objects with an electronic balance. We're going to note the distance M1 falls. We're going to denote that with the letter D, and we're going to measure that with a meter stick. We're going to measure time of fall with a stopwatch. We're going to denote that with a T. And then we're going to calculate acceleration using distance from the meter stick and time from the stopwatch. We can calculate the velocity during each interval by doing distance over, or displacement over, distance over time. And, displacement over time. And then we can calculate acceleration by calculating the change in velocity over change in time. Okay, so now briefly describe the procedure to be used to determine the coefficient of kinetic friction. Provide enough details so that another student could replicate the experiment. Include any steps necessary to reduce experimental uncertainty. So we're going to need to first place block M2 on the table, attach one end of a string to block M2 and pass the other end over the pulley, attach block M1 to the string hanging off the end of the table. Then for each trial, adjust the mass of M1 by adding the additional masses M. Record M1 plus M, the total hanging mass. Do that for each trial. Mark a distance of D, and then release M1 and use stopwatch to measure time it takes for M1 to fall a distance of D. Use distance and time to calculate acceleration, and then set up force equations. So let's go through and let's set up these force equations. So for block M1, the stuff that makes it go minus stuff holding back, M1G minus our tension force, and then that's going to equal mass times acceleration. For M2, our tension force is the stuff making it go. So, and then minus our frictional force. Okay, so now we can solve for tension force and then substitute tension back into the equation. So the force of tension equals M1G minus M1 plus times A. And then we're going to plug this in down here. Try to figure out what mu is. And we're going to do m1g minus minus mu m2, and it's got kind of sloppy. And then that's going to equal m2a. And then we can isolate for mu and try to do it on your own. I already did it on paper, so I'm not going to go through all the steps, but feel free to pause and go do it. And then we're going to find that mu m1g minus m2a over m2j. M2g, sorry. Okay. So then we can set up our force equations. We can figure out mu, and then we're going to perform multiple trials with different masses, record acceleration for each trial, and then we can plot our values on a graph. And then it says which quantities would be graphed on the vertical and horizontal axes to produce a graph that could be used to determine the coefficient of kinetic friction. Well, what I would do is I would graph the m1 plus m on the horizontal axis, or x-axis, and then I would plot acceleration on the y-axis. Okay, and I would do this because by doing this, we could take the integral of this graph, and the integral of this graph, the area under the curve, would be m1 plus m times a. And m1 plus m times a, and this is answering part D too, it's saying describe which information on the graph described part C would allow us to figure out mu. I should draw a little k in front of mu, kinetic coefficient of friction. Well, if we take the integral of this graph, we can figure out what m1 plus m times a is. So if we can figure out m1 plus m times a, that would significantly help us figure out what our coefficient of kinetic friction is. And then we also are going to measure m1 and m2 from our from the electronic balance in our experiment. So then it's going to let us calculate our coefficient of kinetic friction. And we could, just by looking at it, if we see the integral is a very large, if we could recognize that a larger integral, meaning this is larger, that would mean more area under the curve creates a bigger coefficient of kinetic friction, because it would make our numerator larger. So, yeah, I would take the integral of that graph. And now the last part of the question is asking us, the last part asks us about this. The second experiment, okay, once you read it, we can get started. So we are going to have to set up our sum of forces. So for M1, our sum of forces is going to be M1G minus our, so now we have different tensions. So we're going to have M1G minus TV equals M1A. And then we're going to have TH, the stuff making it go, minus stuff holding back, mu M2G equals M2A. Excuse me. Okay. And the acceleration of these two blocks are the same because it says the mass of the string is negligible. So we can figure out we could isolate the tensions. TV equals M1G minus M1A. And then TH plus M2A. Okay, well, we know that M1G must be larger than TH because it's given that it's accelerating downward. So the only way it can accelerate downward is if M1G is larger than TH. And if M1G is larger than TH, that would mean that TVE has to be larger than TH because M1G is the positive integer. So if that's larger than TH, then TV must be larger than TH. And so the answer would be greater than. And that is the fourth FRQ, just one more to go, and then all the videos will be complete. All right, thank you.